Just before we get started, I'd like to apologise for the delay in me putting out content. I promised Susik and Thoggy that I put out content on a fairly regular basis on science videos. Fortunately, I have been quite ill. I've had problems with depression, which has led to problems with the medication I've taken, which has led to problems with my eyes. That's been a wild ride. I've also been quite busy. I've actually got a job interview tomorrow and doing this as a little bit of rest from practicing the presentation for that. Is doing a presentation for you guys, which is a lot less serious. Meh. It's probably going to be a lot longer as well, to be fair. But yeah, if you saw Susik's promotional per Mondays about me, then you know that I'm trying to do more science videos. So, yeah. I thought though I'd start with something fairly simple and straightforward. So, apologies if it comes across a little condescending. For those of you who don't know what that means I'd be talking down to you. But yeah, I thought we'd start out looking at different states of matter. I assume that you're familiar with the standard three states of matter. Solid, liquid, and gas. You know, these are the ones that are within reach at the moment, no doubt. And they kind of suffice for your awareness on a daily basis. They're pretty much what you need to get by on a daily basis, unless you want to live, I guess. I wouldn't advise staring up at the sun during the day. That's a really bad idea, and it's a good way to mess up your vision. But instead, wait until a clear night, if you ever get the chance, and stare at one distant star. You'll have done this before. Now, think about that. There's more material in that star than there is on Earth by a huge margin. And it's largely composed of material in a state of matter that doesn't fit in with solid, liquid, or gas. It's plasma, an additional state. Now, we know that solids melt into liquids, and then when we heat liquids, they turn into gases. But where do plasmas fit in? Well, plasma is actually the state of matter that's hotter than a gas. And when there are some examples other than stars, for example, that are closer to home. If you have a gas cooker or a cigarette lighter, the flame is generally hot enough to form a plasma when it heats the air around it. So in order to do this, plasmas, they're sort of a soup of ionic material. They get heated so much from the gaseous state that they actually lose electrons and become like an ionic stew. But think about plasmas, they're all well and good. Not to touch, though you'll probably get badly hurt. But then we have four states of matter, surely. Well, no, not really. Take helium. Pretty common in the universe, as it's formed by fusion of hydrogen atoms under huge pressure in stars. It's how we get all that energy to make the surroundings into a plasma. Heat the Earth, and then burn my ever-growing forehead. Helium's the lightest of the noble gases. That's these guys over here. Which don't generally tend to form compounds. Some do, but that's a story for a different time. They usually exist as monatomic cloud in the gaseous state when we encounter them. Helium, hangs around in balloons and making your voice very, very squeaky. And it exists as a gas to very, very low temperatures because there's not really any intermolecular forces to hold it together. See, but it's almost surprising that it can exist in a liquid state. It begins to boil at around about 4.5 Kelvin, so that's 4.5 degrees above absolute zero. The melting point of solid helium is even lower. It sits at a nice, snugly warm 1.15 Kelvin. So for realistic purposes, you're not going to find it in the solid liquid states. Also, fun fact, by the way, helium is named for Helios, as in the sun, because it was first detected in the radiation spectrum of the sun rather than here on Earth. Now, admittedly, helium does have the previously mentioned four states of matter, but what about carbon dioxide? Again, it can exist as a liquid, but this requires a special set of circumstances, for example, very high pressures. The general trend of carbon dioxide would go straight from the solid phase to the gaseous phase, and a process known as sublimation. Again, you can argue that I've introduced a bit of a cop-out here, but it does bring us to another point. The conditions for phases to exist does depend on more than the temperature. Take it we all know what ice is, right? This is due to the way, it's less dense than water, we all know that. This is due to the way the molecules packed together and the solid based around the arrangement of hydrogen bonds. Again, I'll cover this at some point later. You can see that in this image you've got the iceberg made out of ice, you've got liquid water that's floating on, and in the air you've got water vapour scattered around. Well, ice can exist in different forms. Standard ice, we all know well, we put in our drinks on a summer's day and then complain about when we slip it on it during the winter. Also has a friend in the guise of amorphous ice. Amorphous ice is generally formed when it freezes too fast for it to form a crystalline lattice, like the normal ice we have in our freezers, or at the poles, for now. It can be generally found in space, particularly in stellar regions. There are multiple forms of ice, actually, which I may cover some other time, but there are actually multiple forms of amorphous ice in interstellar space, which tend to be classified by their densities. Lowest density amorphous ice, though lower in density than liquid water, is far greater in density than crystalline ice. High density amorphous ice can be formed from standard ice we know at colossal pressures, so it's about 1.5 gigapascals at around about 144 Kelvin. High density amorphous ice is more dense than water, around about 1.17 times. However, there is also very high density amorphous ice, around about 1.26 times denser than water. As you can see here, they'll start to sink. However, that's not to say that liquid water has a uniform density. Liquid water generally sits at its densest at around about 4 degrees Celsius. So, we've looked over briefly the four states of matter, which run from the solid state, which just tends to sit as it is, melts into the liquid state, which sloshes around and fits the shape of a container, but isn't readily compressed. This in turn boils into the gaseous state, which fits the volume and shape of a container, features a significant amount of molecular movement, as well as the ability to be compressed, like in pneumatic systems. And then into the plasma state, which is seen when a gas heats up and ionizes, such as in flames or in stars. Or as well, actually, in lightning. Lightning is very, very hot, a lot of energy there. Let's move up from the solid state to the plasma. At each stage, see an increase in the entropy of the system. That's the level of disorder within it. So my desk has very high entropy, and you have to expend energy to reorganize it. I know, tired jokes are tired. But I cannot, hear you ask, what about other things like glass and liquid crystals? We'll come to that in due course, as there are other states of matter to consider. But for now, thank you for watching, thank you for listening. I've been Alan Robert. See you next time.